Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. What are we doing today? We're doing multivariable calculus series. We're in chapter 1, partial derivatives. We're doing section 1.4, which is tangent planes and linear approximation. Tangent planes. And this lecture specifically, we're going to do tangent planes and linear approximation. Let's get to it. All right, so we're going to do a direct comparison. Tangent line to a curve y equals f of x versus the tangent plane to the surface z equals f of x. Again, that's slight abusive notation. Technically, it's the graph of this curve, and it's the graph of this function of two variables, which is the surface or the curve in the plane, which consists of all the ordered pairs x naught, f of x naught. So in one dimension, when we do a function of one variable, we get all the points x, f of x naught give us the graph or the curve gamma in the plane. That curve has a tangent at the point x naught. We have a tangent line, not a tangent plane. That is the tangent plane. Remember, the general equation of a plane or a line is y minus y naught equals mx minus x naught. And then we're like, oh, cleverly, who's m? The derivative. And who's this guy? F of x naught, because it's on our curve. And then we cleverly get this equation. This is LAX, not the airport in Los Angeles. The linearization of x at A, or in this case, we'll put x naught. That is this function. The linearization for a function of one variable is the equation of the tangent plane. Near x naught, x values near x naught are going to have function values which are awfully close to my tangent line values, so I can use this linear approximation to approximate my nonlinear function near these points in one dimension. Same game, but we're in one dimension higher. Now when I have a function of two variables, the graph technically creates a surface S now. At a point on that surface, x naught, y naught, z naught, I get a tangent plane, who's the plane who contains the tangent line in this direction and the tangent line in this direction at that point from the partial derivatives. Again, we cleverly did the same tricks, and we see that those slopes were the partial derivative of f with respect to x and the partial derivative of f with respect to y, and we get the general equation of a tangent plane to our surface. It looks exactly the same. We have one more term though, derivative term, and then plus f of x naught. Now we have derivative with respect to x, derivative with respect to y term, and then f of x naught, y naught, the constant term. Let's do a little bit more. We'll give the specific definition now that you can see what we're doing. Let's give the definition of linearization or linear approximation of a function of two variables, and then we'll do a couple results and some examples. Oh, you're even purring? What are you doing? This is the Black Panther Noodles. Hi, Noodles. He was in the lecture. He just came and tried to interrupt my live lectures last week too, didn't you? Yeah, he's a good boy. All right, so this is the technical definition of linear approximation of a function of two variables near a point x naught, y naught, f of x naught, y naught. What is it? Just like in one dimension, the linearization of a function of two variables is a function of x and y. There they are right there, and it's linear. Every term is either a constant or a multiple of a single variable. These are all. This is a number. This is a number. This is a cat. Kitty, kitty. This is a number. So all this is a linearization. This is the equation of the tangent plane. This is the tangent plane. Just like the linearization of a function of one variable, he's going to jump at you again if you don't pick him up and give him attention. He's about to attack the cameraman too. Therefore, all this says is the linearization of a function of two variables is the tangent plane to the surface at the point x naught, y naught, f of x naught, y naught. And we want to give an analogy of what it means to be differentiable for a function of two variables. So recall a function of one variable. If we have x changes from a to a plus delta x, a small change, then we define this increment, the change in y or delta y, as f of a plus delta x minus f of a. And if f is differentiable, we show that delta y is f prime of a delta x plus some small epsilon delta x. and we have that epsilon goes to 0 as delta x goes to 0. Basically, I'm just squeezing in a differential type version of when we have differentiability, because we want to make sure our function of two variables is differentiable at a point, and then find a linearization at that point for the function. So let's give the two-dimensional analog of that. Let me move this up, or I'm going to basically reiterate this definition for calculus of one variable for a function of two variables now. Let's do that. Okay, moving that up, we see that if we have now for a function of two variables, if x goes from a to a plus delta x, y goes from b to b plus delta y, we define the similar increment delta z to be f of a plus delta x comma b plus delta y minus f of ab. Then we say definition, z, a function of two variables, is called differentiable at a point ab if we can express delta z as this hot mess where epsilon 1 and epsilon 2 now are going to 0, as basically eventually it's going to say that when these disappear, we can write this as the total derivative of this function. Why do we need this? Again, what I'm going to do is don't worry about this so much. What I'm now going to state is a theorem that says you don't have to worry about it. Yeah, you're like, now here's a function, show he's differentiable. You're like, I don't want to, no, don't worry. What we've done is we give you the horrible definition of a differentiable for a function of two variables, and now we're going to give you a theorem which you think is making your life worse, but once you understand what it's saying is, you're never going to have to do this. As long as these first two partial derivatives exist and are continuous, then z is differentiable. So we're going to get a nice condition for, if this happens, then z is differentiable. Therefore, theorem, let z equal f of x, y be a function, and ab be a point in R2. I'm going to assume in our domain. If fx and fy are continuous at AB, then z is differentiable at AB. And then now you go back to the videos on continuity, and then you really appreciate that when we say that rational functions in two variables and polynomials in two variables and trigonometric functions and all of these guys are continuous on their domains. So as long as we compute in examples now, when we do this, we compute the first partial derivatives, we use this theorem that says, yeah, they're these polynomials or whatever they are, so they're continuous at that point. Therefore, because they're continuous at that point, we're differentiable at that point, and we can find the total derivative and find the tangent plane at that point. Sometimes you might have a puncture or a cusp or a sharp point on a surface as well, and then you might not have a tangent plane, because where's it going to be at that cusp? There's problems there as well. So this is just making sure that all of that works out quite well. Let's do some examples. All right, we've got a function f of xy is x e to the xy. We want to show it's differentiable using our theorem, I'm going to guess, not that horrible definition of what the epsilon and the delta x and delta y. No, we're going to use the theorem and show he's differentiable. And then once we have that he's differentiable, we can find the linear approximation of f at the point 1, 0, 1. First of all, what do I need to do to show f is differentiable? I need to compute fx and fy, the partial derivatives, and show that they're continuous at 1, 0. We are going to get fx is going to be equal to the derivative of x is 1, leave that function alone, plus leave x alone, take the derivative of this guy, which is going to be that at, and therefore this is, you could make this look nicer, this is e to the xy, 1 plus xy, and fy is equal to the derivative of this guy with respect to y now, so that is going to be x squared e to the xy. That's a polynomial times an exponential function, and they're continuous on their entire domains, and the domain of those guys is of the entire plane. So these two functions are continuous at their the point, they're continuous everywhere. In particular, they're continuous at the point 1, 0. And so we are going to get that we also have to compute those fx at 1, 0. Oh, first of all, what does that say? Because these are the two partial derivatives I took, and I waved a hand at it basically because I have a polynomial and then times an exponential function. All of those functions are continuous on their domains. The domain here is all of R2, so we have that they're definitely continuous at this point. If my two partial derivatives are continuous at the point 1, 0, f is differentiable, we call it, at the point 1, 0. Now to find the linear approximation of that, what is the linear approximation? It's the tangent plane this time. So that is going to be z equals fx at 1, 0, x minus 1, plus fy at 1, 0, y minus 0, plus f of 1, 0. I write that out for myself as a mantra every time. I've just put my specific point, at least, into the equation of the plane, which is going to be the same every time. And then what I'm going to do is, I've already calculated those. Let's put 1, 0 into both of those and find out what that number is, and what f at 1, 0 is, and then we'll have all of our values. We're almost done. All I need to do is erase quickly that. Here, this says fx at 1, 0 is going to be what? This will be e to the 0 plus 1 times 0 times, it doesn't matter, where I'm going to get 1. F of y at 1, 0 is going to be 1 squared times e to the 1 times 0, which is also a 1. And f of 1, 0 is equal to this 1 times e to the 1 times 0, which is also a 1, 1, 1, 1. Therefore, that's what that means. Even if you want, we can color code. Now, don't be lazy. That one goes here. This one went here. And this one was a square and goes there. There's the equation. This is the linearization. This is L10 of xy. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and many others. I'm the Tutor Wizard. See you next time.